Hello and welcome to the Safer Sim webinar series. Dr. Afifah is here from the University of Central Florida to present on a project she did for Safer Sim. And Dr. Afifah, I'm going to turn the floor over to you.
Thank you, Dawn. Welcome, everyone. Today, I'm going to talk about a project that I worked on, which is on reinforcement learning for optimal speed limit control over network. This project is a combined effort of me and my advisor during my PhD, who is Dr. Xiaomio Guo. So today, first, I will go over the background and the motivation. Then I will discuss the methodology that I've used in the study, and then I will demonstrate some of the results from this study. And finally, I'll conclude this presentation by going over the future studies and the general summary of the whole study. So variable speed limit control can dynamically adjust speed limit in response to traffic condition and regulate traffic flow and reduce congestion. So when vehicles can receive information, so speed limit information, they can make routing decisions. So this decision-making process depends on the rerouting as well as lane changing. So if we look at the picture over here, when this decision-making process happens, there occurs there's a bottleneck that takes place. Plus, when the vehicles are choosing one lane over the other, there is usually an oscillation that is noticed on these routes. So the motivation of this study is to optimally control the speed limit of a route using variable speed limit control, or VSLC, and understand its impact on network mobility and safety and mobility and safety. Further, we also wanted to understand how the VSLC implementation affect the traffic behavior, as well as what incentives should be provided to VSLC to improve network mobility and safety. So we did an extensive literature review, and we found that physical model-based approach were used initially to control the speed limit optimally. However, it requires accurate model of the system, and it faces computational difficulty. Recently, reinforcement learning-based approach has been used, and people have been using this for different traffic scenarios, such as RAM metering, work zone operations, etc. However, most of these projects are for small-scale problems. So the objective over here we set is that we propose a deep reinforcement learning or DRL model to implement VSLC to improve network mobility and safety, considering rerouting behavior of vehicles. We also propose suitable rewards for the DRL model to improve mobility and safety of a network. So we go through the proposed algorithm. Over here, we propose using twin delayed deep deterministic policy gradient. So this is a DRL model. There is another DRL model, which is deep deterministic policy gradient. However, we did not use the DDPG or deep deterministic policy gradient because the DRL, or deep learning reinforcement learning faces the overestimation bias and accumulation error. So in the DRL, overestimation bias occurs when the Q function is estimated. So in DRL, Q function is estimated using neural network. So neural network approximates the Q value. So during this approximation, sometimes it's overestimates. So when the actor is learning using the Q value from the critic network, if the Q value is overestimated, the actor function will also generate some error into the model. Another error that we face is the accumulation error. So the accumulation errors is when we compute the Q value, which depends on the next Q value, as shown over here. So in each Q value, at the end of it, there is an error that gets added. Over time, this error kind of accumulates and causes this accumulation error. So here's the structure of the twin delayed deep deterministic policy gradient. And I will go over the difference between the DDPG and the TD3, or the twin delayed deep deterministic policy gradient. So we have actor network and critic network. The difference between the DDPG and TD3 is the TD3 have two critic networks as shown over here. So we have online network and then target network. So in each step, the state, action, reward, and the next state gets stored, and a sample is taken and passed into actor and critic network. The first activity takes place in critic network. So we said that we have two critic network over here. So we find the two critic network by adding some noise into it, as shown over here. And then we also said that the TD3 kind of reduces the accumulation and overestimation error. One of it's done using the target Y. So in target Y, this is a Bellman equation. And over here, we take the minimum of the target critical as shown over here. And then we update the critic network, online critic network, using this formula shown over here. Next, we discuss the actor critic network. Over here, the actor critic network is updated using this formula shown over here. And the difference between the DDPG and TD3, one of the other differences is that the actor network is less frequently updated than the critic network, which helps with the overestimation and accumulation error. Finally, we have target actor network update and target critic network update. We use this formula, which is this is updated using a soft update, and this is also updated less frequently. We also have some exploration. So the benefit of using DDPG or TD3 model is it's an off-policy network, off-policy method. So off-policy method means the exploration can take place outside the learning. Over here, we have used the Laplacian process as shown over here. We also need to define the state, action, and reward. For our problem, we have occupancy of each network, each link as the state. We have action set as shown over here, where the minimum action is 30 and maximum action is 65 miles per hour. And for reward, to improve network safety, we use the log of TTC. So now the TTC is time to collision, which is defined as the estimated time it will take for two vehicles to collide if they maintain their current trajectory and speed. We use log TTC. This is because when the TTC is smaller, it will be penalized and it will encourage the TTC to be higher. To improve network mobility, we use total travel time, which is defined as the accumulation of current travel time on an edge times the number of vehicles on that edge. And then we also estimate the traffic oscillation dampening. For this, we use the difference between the relative difference between the number of vehicles in one route and the second route, and the number of vehicles in the second route. We have used Sumo for our problem, and we have defined some attributes for the configuration. One of the important attributes is the rerouting of vehicles, which we have defined using this formula. Now let's discuss some experimental results. This is the network that we used. We used a small network so that we can understand the traffic behavior well. Over here, we have a base case, which is the link 2-3. So we control one of the route, and we control one of the link of this route. So route 1 is controlled. First, we only show some of the results in this study, and we first show our model with other models that are out there. And it shows that the DDPG that we talked about before, it performs the best when it comes to network safety. So it improves safety by the safety is improved 4.5% higher than the base case. However, the TD3 that we used, that also improves safety quite better. It's 3.84% higher than the base case. So the base case is the VSLC, no VSLC set. However, when we look at the network mobility, we can see that the TD3 performs the best results among all the methods that we have shown over here. Other than this, we also show the DQL or deep Q learning approach, and it performs the worst for network safety and mobility. This is because deep Q learning uses discrete action, and whereas the SAC or soft actor critic or DDPG and TD3, they use continuous action. So the discrete action, you need to run the model longer to make the model perform better. Next, we discussed the assessment of different traffic control. So we also did this study to understand different control strategies. We have no VSLC if there is no variable speed limit control implemented. And then we have traffic engineering practice. So this is defined as if the traffic engineers can't control the routes, and they can control it in such a way that both of the routes are occupied at the same time. So it's essentially just dampening the oscillation that takes place in the route. And then we have variable speed limit control implementation to improve network mobility and also to improve network safety. So we first go through the results for the routing. This is for the no VSLC, no variable speed limit control implementation. We implement the same speed limit, which is 40 for both routes, both of this route. And we can see an oscillation that takes place in link 2.3 and link 2.4. How do we know that? We see if we notice in link 2.3. Now I'm going to show this links again. So link 2.3 and link 2.4. So when the routing takes place, it shows that when the occupancy is highest in link 2.3, it's the lowest in link 2.4. So it's essentially just the traffic is oscillating, taking one route and then taking the others, not simultaneously. So we eliminate that using this traffic engineering practice as we discussed. As you can see, the variable speed limit is quite wild across the link 2.3. So the link 2.3 is this one, the base case. And the other link is the constant link, 40 miles per hour. This strategy shows that both of the links are occupied at the same time. We know this by seeing that no links touches the zero occupancy. Then we have variable speed limit control for improving mobility. So it's mobility. So it shows that higher speed limit is better in this case. And we also see that since the link 2.3, we implement this variable speed limit control, and link 2.4, it's a constant speed limit. We can see that more vehicle is attracted to link 2.3, so route 1, and less vehicles goes through link 2.4 to go to their destination. And then we have variable speed limit control implementation to improve network safety. So over here, the control provides lower speed limit. Because of that, more vehicle tends to use link 2.4 as shown over here. Now let's go over the results for network mobility. We can see that for the 4 traffic control strategies, variable speed limit control to implement network mobility performs the most highest result for network mobility. So over here, the total travel time is 28.43% lower than the base case. And we can also see that the average queue in the first link is the lowest among all the strategies. We see the traffic engineering practice over here, and we see that it's higher because both of the routes are occupied. So the queue in the first link is higher because the vehicles need to decide which route to take. And we can also see this in this figure, the Q length. Then we go over the results for network safety. Over here, we can see that traffic engineering practice have a higher safety, which is 5.5% higher. But if we look closely, we can see that there is a lot of lane change activity that takes place on this in this strategy, which also contributes to the log TTC as shown over here. Compared to that, when we see that variable speed limit implementation for safety, we can see that the log TTC is also quite high, 5.18% higher than the base case. And we also noticed that the emergency brake pressed during this strategy is the lowest among all the strategies. We assess our model's generability capability. So we assess that using some traffic and driving behavior so we use the OD demand, we use LC speed gain, or which is lane change to speed gain. And then we use speed factor. We use the mean and the deviation of the speed factor. So speed factor is something that each vehicle is like in Sumo, we multiply the speed factor with the speed limit. So the speed factor is random, and then it just gets implemented in each of the vehicles, so they can have some randomness into it. We showed the results for OD demand and LC speed gain, and we can see that the model actually performs pretty well for all the cases. If we give an example, for example, for the OD demand, it shows that as the OD demand increases, the model can learn better compared to the no VSLC. As well as in the mobility cases, we can see that the mobility is decreasing as the OD is improving, OD is increasing, and our model can adapt to that. The final result we're going to show is the sensitivity of variable speed limit control in the network. So it's a small network. So what we did is we placed the variable speed limit in different positions. We placed it in link 1, 2, which is the first link. And then we have the base case, which is the link 2, 3. We also divided the first link to upstream and downstream and wanted to see its behavior. And the same was done for the base case. Now, we didn't put the variable speed limit control for the other link, which is 2, 4. This is because this will behave the same way as the base case. So this is the results for the safety improvement for the variable speed limit control. And it shows the performance of all the strategies shown in the previous figures. We wanted to understand the behavior of the model. So what we did is we took sample of the some random samples from this, and we generated this table over here. We showed the mean and the standard deviation over here. We'll go over 2 strategies. This is the first one is the base case. So when there is like we put the variable speed limit control over here, right over here. So it shows that when the speed is lower than the constant speed, most of the vehicles are taking the second route to go to their destination. There is also a queue of 306 meter. We also noticed some behavior, which is the number of aggressive drivers in the system, as well as the number of emergency brake pressed during this system. Compared to that, the best case we see is when we divide the variable speed limit control into 2 parts, in the upstream and the downstream. It shows that there is a differential speed limit across this link right now. This provides a better results than the previous one. The reason we see is like first, the routing is similar in both cases, nearly similar in both cases, because these are like the same speed limit use. Now, since the vehicles, there is a queue that is forming over here, the speed limit is quite higher, and since vehicles are arriving from this stream, this speed limit is lower. So this actually helps with the result, with the safety results. And the Q formation is higher in this section, obviously, which is 360 meter. This is much higher than the base case. We also noticed that the aggressive driver behavior in the system is 10.7% lower than the base case, the previous case that I showed. And the emergency brake pressed during this system is 78.4% lower than the base case. So this is the whole, we just showed a sample of the results. For more, you can see in the paper. So let's discuss what we have seen in this study. So we proposed a DRL model for optimal speed, optimal control of the variable speed limits to improve network mobility and safety, and we considered rerouting behavior of vehicles. We demonstrated the generability of the control algorithm across different traffic behaviors and driving behaviors attributes. And we also compared that with state-of-the-art DRL models. We assessed the efficacy of various traffic control algorithms and analyzed the spatial distribution of variable speed limit implementations with a focus to improve network mobility and safety. Right now, we are trying to implement this model for a larger network. Now, this is quite difficult because for large network, there is like two actions taking place at the same time. So we first tried it with the two actions is we first need to identify which location you want to implement the variable speed limit control, which in this study we have done by manually putting the variable speed limit control. And the second action would be finding the speed limits for those positions. So this is quite a difficult situation we have right now, but we have successfully come up with a solution. We first tried a static model, but since it's a dynamic project, static model will not actually give you a proper result. So we used a reinforcement learning model, and this was a hard thing to do, but we have accomplished this. And then the second thing we are working on is also implementing we have shown the network mobility and safety results separately. We're trying to generate objective that includes both the mobility and safety of the network. So that's all from me. Thank you everyone for listening. If you have any question, you can contact me.
Thank you. Would you like the opportunity to provide your contact information aloud?
Yeah, it's F8235508 @ucf.edu.
Thank you very much for that excellent presentation.